I still have time to interact as well. So just put yourself on mute. It's all yours, Dr. Gamble.
Okay, so happy to see everybody. Okay, if we were here in person, then I'd have everybody stretch out. It's the end of the day. I know it's been a long Wednesday, but I guarantee you we're gonna have some fun. Um, and we're hopefully we'll do a little bit of coding today. Um, so I'm gonna let me share my screen here. Okay, so happy you all could show up. Um, I am Dr. Ronald Gamble. I am a theoretical astrophysicist at NASA Goddard Space Flight Center here in the DC, Maryland area. I am also astronomy faculty at the University of Maryland, College Park. Um, and at NASA, I do research on black holes, and I am also the director of the NASA program called Cosmic Pathfinders. So it takes students kind of like yourself who are in college and it brings them in, gets them skills. We do hackathons, we do meetups, we network. Um, we have a program that allows students to give talks, a lot of engagement there to make you the best scientist that you could be inside the NASA space. So when you get to college, come knock on my door so you can be a part of my program. But today we're going to be touching on what are black holes? What's space-time? What do I mean by the edge of the universe? And what do I mean by decoding black holes? Right? So I'm gonna using the little raise your hand feature on Zoom, raise your hand if you know just anything about black holes. You can just keep the hand up. Okay, so three of you. Okay, cool. About four. Cool, cool, cool. All right. So that means you're smart. That means I don't have to do a whole bunch of talking today, right? So so kind of diving into this, right? I borrowed a couple a presentation that I gave and I modified one to not give you a bunch of boring equations and everything else. So I turned everything into like a comic book. Everybody likes comic books. I'm sure you've all seen a Marvel movie, read a comic or something, right? But here is a some information about black holes, about what I do, right? And then once we get through all of this, we're actually going to see how you can actually code up a black hole on the computer. What does a black hole look like on the computer? So I said what I do. This is a very quick reemphasis of my title or position at NASA. I spent a lot of time in school getting here, and I'm going to touch on kind of like my NASA journey in a little bit here, but I kind of want to emphasize that, being a theoretical astrophysicist means that you get to do a lot of cool science in a very cool way, right? We may not have a bunch of fancy labs, and there are some for the people who do experimental things, but I use computers, codes, I write on chalkboards, which you can clearly see behind me, and I use whiteboards and I use a whole bunch of math to tell me a story about what nature is doing. What is nature doing around black holes? How is nature folding and curving space-time? What is space-time? And so trying to answer some of those questions is my job at NASA, and especially having them around very special objects that we call quasars. So to keep going, this is kind of where my journey started. Yes, that is me on the left. I believe I was in about fourth grade. Um, that was when, I started asking all these weird questions. Does the sun have fire? Why is the night sky dark, but the stars are bright? All of these different questions. And my mom couldn't answer but a fraction of those. Her degree is in biology. She went to Fordham University, and she codes for a living. So she's a software engineer, but she's not a physicist, right? She didn't study astrophysics. So I had all these questions. And so I had to go to college to kind of feed my curiosity. In college, I was always asking my professors, my advisors, my mentors, my teachers, why? Why this? Why that? Why these equations? How come these equations don't work the way you said they would? And why don't we have answers to some of these questions, right? And so this is where the theory aspect, and theory just means discovery, right? So I am a scientist that works to discover new science. That is a theoretical physicist. And so I went to North Carolina A&T State University. If you know of them, go Aggies. Um, I got my bachelor's of science. This is kind of like when we say we go to college, that's what we do. It's called undergrad. Um, After that, I stayed at A&T. And I got a master's in experimental physics. So I worked on very intricate things that we call thin films and other materials, quantum materials that we call superconductors. If you've ever ridden a train or you've ridden in a Tesla or any electric car, you have interacted with that type of magnetic material. And that's what I studied in grad school for my master's degree. Now, for my doctorate of philosophy, my PhD, right, I studied a thing called gravitational waves. If you've ever seen the image of LIGO, it's an abbreviation for the Laser Interferometer Gravitational Wave Observatory, LIGO, LIGO. Look that up. I worked on some of the LIGO data. I used that data in my graduate work. There's going to be a new observatory that NASA will be launching in about 30 years. So by the time you're good and done with school and grad school, you could be working for NASA too, working on gravitational waves, and helping me prove some of my research in grad school. Now, at A&T, I was the very first one to get a PhD in astrophysics. So you can go look that up. If you look for my dissertation, you'll find it in the library. It's printed. It's about 200 pages of mathematics and physics. I used a thing called general relativity. If you've ever heard of Einstein or relativity, all that, that's what I used in my dissertation. That's what I use every day to study my science of black holes. So that's me on the right. About a month after I graduated, after I finished, we wear these big, heavy robes. It was hot that day because it was the summer, but I had to wear it to take pictures so I can show my mom, and she was very happy, taking me from fourth grade to PhD. So now to give you kind of like a much broader outlook, right? This is what I call a career map. Where did I start? I was born in Dayton, Ohio. Go Buckeyes. I grew up in Raleigh, North Carolina. You can see everything that I did at North Carolina A&T. I also taught there. I designed courses there. I did a whole bunch of things, right? But when I left, here are the things that people don't tell you when you're progressing through your career. I was unemployed when I left A&T. And you can imagine, okay, well, you have this fancy degree, you study these weird things, you have all these math skills, you've coded in 12 different languages, you have 3 degrees in physics. Why didn't I get a job? Well, at the time, the nation itself had a deficit in hiring scientists like myself. Why? Because there wasn't a trend in it. There wasn't a boost in some of the research that we have today. And I'm talking, this is pre-COVID, so this is a while ago, right? But I was recruited by the Defense Threat Reduction Agency. So that was my next position. This is something called a postdoctoral fellowship that you get when you finish grad school or your PhD. Um, It is kind of like an introductory job to get you into the field of whatever you study, right? So you can think of it as an entry level job. And I know you need a PhD for it, but this is how much we have to learn, how much we stay in school, how much we have to train just to get our first job. Um, and yes, as you can see on the slide, what I did there was classified. So I did have a classification of some kind. And then you hear that in movies where the scientist has a secret, top secret, super secret, something classification. Those are real. And I had one of those, and I worked on some weird things as part of that agency. And it was a fun job to have, but it wasn't the dream job, right? The dream job was always to get to NASA. Um, and I got to NASA, dream job secured in 2021. Yes, as we were still in a pandemic, but I was recruited by NASA. So even along that journey, even through me looking for jobs, even through me driving Lyft, if you've ever ridden in Lyft or Uber, I've done that before with my PhD. This is the real story, right? So I'm not giving you any fluff. I'm not skipping over anything. This is exactly how I got there. Trials, tribulation, dreams. I cried, I bled. Um, I worked hard. There was a lot of sleepless nights. Um, but I can say at that bottom left corner, dream job secured. I am a NASA theoretical astrophysicist. Um, Now, what do I do at NASA? So I do a lot of research that I just mentioned, but again, I'm going to emphasize here in white. I mentor a lot of minority students that look like me, that talk like me. Uh, my father's family's from Panama, so I am Latino. My mother's family is from the US, so I'm Black. I am both. And so I like to mentor. I devote my part of my career to mentoring those students coming up and mentoring other students who have an interest in astrophysics who may not have some of the resources that you get at these much, much larger institutions. Students that are coming from kind of similar backgrounds as I did. Um, I grew up in a single parent home. My parents divorced when I was 5, so it was tough, right? So, and I didn't see scientists like myself until I got to grad school, until I got to college. You didn't see that. I didn't see that as a child. So I was really in the dark trying to figure this out. What's next? I don't know. That's part of the journey. You don't know what's coming next, but you're going to put one foot in front of the other. I hope that my research does win me a Nobel Prize one day. Fingers crossed. Um, but again, you can't get to a place that you can only get to a place if you do the work. And part of doing the work means that you have to put your head down, right? You have to learn things that you haven't learned before. If you're struggling in math, don't fret. I had to pass. I failed one math class in college 3 times. And now I'm here teaching you, showing you how to study black holes using relativity and all these funky mathematics. So you can do it, stick to it, and then you can kind of see, where your journey has taken you. So this is kind of like a pictorial version of what I just showed you. You might recognize that woman down at the bottom. Um, some of your parents might know her, but if you've heard of the show called A Different World, that is the actress Dawn Lewis, a very good friend of mine. So along my journey in my career, I have met and I have talked to many different types of people. Yes, I did go to the Quantumania movie premiere in LA last year. It was an amazing, amazing opportunity. And I got invited to go alongside as a guest with my now current partner. Um, so I've spoken 3 times at the White House last year. I've spoken at other various schools. I've traveled the country giving talks, showing them representation, showing them that yes, there are many different types of astrophysicists, and we come in all different shapes, colors, sizes, language. That flag in the bottom left corner, that is the Panamanian flag. So I take my culture with me everywhere. The picture of the bird, I'm an artist. I painted that. Um, some of the art that you might see behind me, I painted that as well. So I'm an artist and a scientist at the same time. And I have sold artwork across the globe, internationally. So you can do both. Whoever tells you you can't, do not listen to them. You can do both. Prove them wrong. You see it right here. You can totally do both. Now, well, where am I going? I have no idea yet. Again, if Iron Man can defeat Thanos, then I guess I can win a Nobel Prize. It's easier said than done, right? But we hear things like the sky's the limit, break your glass ceiling. Uh, if no one's done it before, why can't you be the first? Uh, all of those things that we keep saying, and then again, we say these things, we say these things, and we say these things, and they're easy when we say them until you actually have to do it. So part of me here today is showing you that if you have a dream, if you have an aspiration, if you have a passion for something, pursue it. If your friends aren't doing it, do it anyway, because you want to do it. None of my friends studied astrophysics, even some in college. We were in physics, but none of them studied black holes. They said it was too hard. I stuck with it, and now I'm here. And now they're asking me for NASA t-shirts and backpacks and stickers. But again, sticking with it is part of the journey. So now we're going to transition here to diving into some of the science, right? And I told you these slides are like a comic book, but the comic book is animated. So very quickly, if I had to say what I do on a daily basis, this is what I do, right? I theorize scientifically plausible predictions of new physics describing black holes, quasars, a thing called relativistic jets, um, and using complex mathematics and analogies, right, with other naturally occurring phenomena. So basically what that means is I use a lot of math, but I also study other areas of nature to make analogies back to the physics, back to how we can describe black holes using something like hurricanes, using something like tornadoes, using something like the water going down your drain pipe. Those are some of the phenomena. So those are some of the naturally things that occur that I study in conjunction with black holes so I can understand nature better. You have to understand other areas of nature if you're going to understand the mysteries of it. So I use a combination of supercomputers, data that comes from very, very large telescopes like James Webb and Hubble Space Telescope, and other observatories. I use computers that are about the size of your bedroom. I also use smaller computers like my laptop we're using today. But I use a combination of a bunch of different things, right, to give us a tell a story, to give solutions to some of these mysteries that we're trying to figure out. Now, there we go. Now, if you were to ask me, okay, well, what does a black hole actually look like? We're going to keep diving. We're going to move a little quicker here. What does a black hole actually look like? Well, it's going to look like this a little bit. And those green streaks, you can imagine them being little particles, right? Things like electrons, atoms, protons, all those things that we've heard of. All those things are wisping around a black hole. Now, one other thing that I would like for you to know, a black hole, oops, a black hole is not a funnel. I know you see that image, and I do not have that image on here today, but a black hole is not a funnel. It is a sphere, right? And we're going to actually see that coded up today. It is a sphere, not a funnel. So the little hole in space-time that you might see, you Google black hole and you see this little funnel shape. That's not the actual picture of a black hole. It's a sphere. So keep that image in your head. We're going to come back to that. Now, again, I'm not going to sugarcoat anything. I want you to learn the actual terms, the real language, so that when you go home, when you go to school, you talk to your friends, you can tell them the real story, the real terms. These are things that we use every day, the professionals, so that you can sound like a professional as well, right? You don't have to wait until you have gray hair in your beard like I have to start speaking like a scientist. Speak like a scientist today. So I'm not going to go super, super deep into this, and I know this looks like a whole bunch of foreign language, but we take math on the left and we translate it into geometry, science, physics on the right. That is what Einstein did. That's what I do. So now, as you can see, don't ask me what's inside of a black hole or my coffee pot, because I haven't seen either of them in a while. But you can see that the black hole is a sphere, right? And so everything that you're seeing on the slide right now, those two images, that is data. That's not a picture. It's not something we drew. That is real data. You're looking at about 10 million data points right there, 10 million dots on a graph. Again, this is just illustrating some of the things that I use every day. So you're seeing part of my work. This is what we do every day as a theoretical astrophysicist studying black holes. We have to translate math into words, right? How can I describe these equations into words? I learned how to intricately do that in school. When I was learning my science, when I was learning about black holes, I had my textbook next to me. I had a computer screen in front, and to the other side, I had a notebook. And I translated the mathematical equations into words, and I did it back and forth. That is how I learned my math. That's how I got good, to the point where now I'm doing this math in my head very quickly. So it took a while to get there, but once you get there, then you can start doing the math very fast. Now, we mentioned something called a relativistic jet. You see that beam coming off? Those are the things that I study at NASA. So these things are coming off the center of our galaxies. They're coming off of other galaxies. But as you can see, there are a lot of different properties for these objects in space, and they are very, very bright. You can think of, even if you look at the sun, it's 10,000 times brighter than the sun, if you can imagine it. So these are very bright objects, very fast objects. We're talking about them traveling at the speed of light. So this is extremely fast, extremely bright, extremely energetic, right? These are whole galaxies, and if you were to go near one, it might look like this. So again, this is not a hole in space, but this is a sphere. So you can imagine a black sphere. If you hold a black marble, that's what a black hole would look like. But if you look at the very edge, it bends light around it. You're looking at the bending of space-time. All of these equations that you just saw, it describes the bending of space-time. So again, this is what I study at NASA. How does light bend beyond the black hole? And there's a little narrative. This guy, pay attention to him in this presentation of slides. He's going to try to capture the energy of a black hole, and he probably fails because you can't do it. Now, in the bottom left corner, that is a section of my code. If you ask me how many coding languages I know, you can throw it in the chat. I'm going to answer it right now. I know 12. 12 coding languages. 12. We're not going to go through all 12 today, but we're going to go through one of them today. So now, kind of pivoting. 7's close. Add 5. Now to pivot, you're looking at real data. So again, I'm not just going to talk about what I do. I'm going to show you what I do every day. So this is what we do as a physicist, as an astrophysicist every day, studying black holes. This is what we do. And do I break supercomputers? Yes. In my lifetime, I have broken 2 supercomputers. Now you can imagine it's very hard to do, yes. But I have broken 2, and I had to fix both of them. So if you break it, you got to learn how to fix it. That was our rule in grad school. If you break it, you got to learn how to fix it. Now I can go to NASA and say, hey, I know how to fix your supercomputer. So again, we're turning our trials into skills. That's exactly what I did. Now pay attention to these 2 graphs here, because we are going to recreate these today. We're recreating these today. So to go through these very quickly, again, I'm showing you real work here. This is real work. right? So these are no longer just graphical images. These are no longer just illustrations. You're looking at real work that I'm actively working on. And yes, I have to fix my code after this talk because I broke it right before we got on. But again, to illustrate, what do? I am always trying to convince people Fortran is the way to go. Some of your parents might know Fortran. And if they have, kudos to them. If you've heard of Fortran, kudos to you. I think it's the best language. Keep going. That is a real blazar that I look at. So now, again, back to this idea of relativistic jets. These are these astrophysical objects, right? And they come off of what we call astrophysical black holes. These are black holes that are not of the theoretical variety, right? These are real ones. So these are black holes that are at the centers of galaxies. So we're looking at whole galaxies. We're trying to observe X-ray light, gamma ray light, visible light, infrared, radio waves, microwaves, ultraviolet. We're looking at all of them to give us an idea, to tell us a story, to give us solutions to what nature's telling us around black holes. How do black holes behave? Now, if you look at this, what looks like code, TXX0506 plus 056, and I'm going to put that in the chat here. I want you to Google that after this talk. This is what we call a blazar. Look up that blazar after this talk. It is a very energetic, very weird, very, very bright object that I am looking at that is hundreds, if not thousands of millions, excuse me, of light years away. So that is a blazar that is millions of light years away, right? Hundreds of thousands to millions of light years away. And we're taking pictures of it. How can light reach us from a million light years away? Meaning it's going to take 100,000, thousands, if not millions of years for that light to hit our telescopes. So we're looking at the past. Every time you look up in the sky, even tonight, you're looking at the past. You're looking at light coming to you from the past. Some of those stars may not be there. And some of those stars are actually galaxies, and you may not know it. This is one of the wonders for studying astrophysics. So now, again, there's some of the brightest, most energetic objects in the known universe. This animation at the bottom, again, if you could imagine all these energetic particles wisping around this blazar, that's what it might look like. And at the very center is the black hole. Why is it so bright? Well, particles emit radiation. This is how your light bulb works. You're looking at energetic particles. This is how the light from the sun works. This is how solar panels work, solar energy, right? This is how plants get their energy from the sun. This is how your skin gets melanated from energy from the sun. This is all energy from light. This is all light hitting everything. So that's kind of what we study, right? So now, again, back to this guy in this comic book, trying to capture the energy of a black hole. You cannot do it. And what happens if you try? Catastrophe. Now, again, this is a comic book, right? This is comical. Have we ever been to a black hole? No. Can we get to one? No, they're too far away. If we were to ever get to one, could we capture the energy? No. A lot of no questions. Could we fly through one? I'm going to say no. Could you throw stuff inside of a black hole? You can, but you can't get it out, right? So again, these are the mysteries of studying black holes. We don't know what's inside of them. We don't know if we can go in and out of one. We don't even know if we can travel to one yet. So, but I do know if you go to a black hole, you're going to see an explosion of that kind in the bottom right corner. And this is what we call a blazar. So you go type in that blazar TXX0506, you're going to see something like that, but it's going to be a real image. You'll see a real explosion in space. And that's what it looks like, right? So you're seeing this is an actual picture of a black hole. This is a galaxy shining directly at our telescopes. This is what's called a blazar, right? So to kind of wrap up this, kind of wrap up this little session here. If anybody's interested, if you're going into college, if you're interested in NASA and what we do, reach out to me. This is my program at NASA. And we had a session and an annual astronomy meeting. If you're ever interested in engaging with more scientists, look up the sciencehaven.org. If you've heard of Raven the Science Maven online, Dr. Raven Baxter, my partner, we're in this together. We put together a program that gives 100 telescopes to 100 families with 100 dreams. We just came from Buffalo, New York, giving out telescopes. You can look that up too. Share it with your friends. If you're interested, reach out to us also. Now, the last thing I'm going to say here, and I'm going to leave you with this quote that my mom told me, and it always stuck with me. My mom always said that if you want to become absolutely anything you put your mind to, you can become absolutely anything you put your mind to, whether it's an artist, a scientist, an educator, but just don't forget who you are. So I became all three. I've been an artist. I'm a scientist. I'm an educator. I've taught classes. I've designed classes. I've taught at all stages. I've been a scientist at NASA and other places. I've sold art around our country, excuse me, outside of the country. Never forgot who I was. You never forget where you come from, who your people are, who supported you, who's got your back, who your friends are. Pay attention to those people who don't support you, because they will come knocking. And when you reach all your successes, they'll say, hey, I was with you. No, you weren't. But the ones that sit beside you, the ones that you're friends, the ones that you call family, those are the ones that you need to support. Those are the ones that you should say thank you for supporting me. So to everybody that supported me in my journey, I say thank you. Thank you for everybody who showed up today for this. You can reach out. I would take a screenshot, excuse me, of this slide right here. This is how you can get in contact with me. Some of the organizers for this session today, I know you tracked me down, and I thank you for being adamant of getting me here today, because I am a busy man, but I always make time for talking to students and inspiring the next generation of scientists. So thank you, thank you, thank you. So now we're gonna I'm gonna transition. Does anybody have any questions right now? Any questions? Yes, you can unmute. Camry, you have a question?
Well, I just wanted to ask, like, how did you know you wanted to get into black holes? Because I remember you talked about like you were the only one studying it, but how did you know that was what you wanted to continue doing?
I Googled. Well, back then Google wasn't too strong as it is today, but I looked up online on the internet and in books. What are the unsolved problems in physics? What don't we know yet? That's what sparked my interest in black holes. That's what sparked my interest in things like dark matter, dark energy, space-time, curvature. What are those things? These are very weird concepts that we don't have a lot of answers to. So that's what sparked my interest. And they were hard, they were challenging. I love solving puzzles. I can do puzzles very easily. So that was a thing that I always did as a kid. So this was like a puzzle to me, right? So this looked like something that I could have fun with. So that's how I got interested into black holes. Okay, cool. Any other questions? We kind of
We
move on
have
to the
a
last thing here.
question in the chat.
Okay.
Camry asks, who is Raven Baxter?
Oh my gosh. So she is an amazing. I'm gonna try not to blush here. So that's my partner. Um, but she is a molecular biologist. So she is a PhD scientist like myself. And you could imagine our household is a bunch of nerds walking around talking science. This is what we do all day. But she is not studying black holes, but she does a lot of stuff called science communication. So she engages the public, right? She's traveled all over the place, if not all over the globe, of talking to science and doing exactly what we're doing today, engaging people in the science, getting them educated, telling them about kind of digesting and reiterating things in normal language, right? So day-to-day language, not a whole bunch of jargon or abbreviations or acronyms like we like to say, but in language that you can understand. What is molecular biology? What is physics? What's astronomy? What are black holes? Stuff like that. So you can Google her, Dr. Raven Baxter. I encourage you to Google her. Don't just know me, know her, and know our friends as well. Any other questions before we transition? No more questions. Okay, who's ready to code? Just throw up a hand or make some noise. Okay. All right, so now I'm gonna show you this. Okay, so now, excuse me, what we're going to do today, all right, and Miss Ponder, if you can give me a time check really fast. How much time do we have left?
You you have until 7:30, so it's only 6:43.
Oh, I went so fast. Okay, cool. We have plenty of time then. All right. So we're going to deep dive. We're going to dive into the actual code, right? This is what a black hole actually looks like when you solve the equations by hand and then you type them up on the computer. What does it look like, right? What does a black hole look like? So now today, you're going to help me code this up. So I need for you all to be kind of active in the chat. You're going to throw some numbers in the chat. Tell me to dial, move these dials up or down, left, right, spin the black hole, all of that. So we can get some pictures. We're going to generate the data, and then I'm going to send it to you because that would be your data now. You helped me generate this data today. So you can go home, you can print it out and say, you created a black hole on the computer. Now, couple things here, right? One thing is that we've got 3 different types of black holes. I know, 3 different types of black holes. One type of black hole is what we call a Schwarzschild black hole. It's a non-rotating, non-charged black hole. What do we mean by that? We mean that the black hole, it doesn't spin. The Earth spins on an axis, the sun spins on an axis, Jupiter, Mars, all these planets, our Milky Way galaxy spins, right? But there is an approximation to studying black holes. To make the math a little easier for us, we turn the spin off. Just in the math. Now, do these black holes actually exist in nature? Not entirely. I think we have a very good idea to say that all black holes spin. Now, why are we studying non-rotating black holes, non-spinning black holes? it gives us an idea of what else happens around the black hole. We simplify some things. As soon as you start spinning around like an ice skater, if you're on skates, everything gets so complex, everything gets complicated once you start rotating around. The second type is what we call a rotating black hole or a Kerr black hole, right? So this is a black hole that has no other charges around it, right? It's not generating electricity or magnetism, just rotating. These are the closest to astrophysical black holes. These are the real black holes that you saw in the picture. Those are the closest. There is a third kind called a Kerr-Newman black hole. And all of these titles for the black holes are names of people that helped discover the solutions to these black holes. They worked out the math. It took them years and years to work out the math. When you discover something new in physics, you get to name it after yourself. So these people worked on the mathematics to give us a description of what the black hole was doing, right? Now, if I go back up here and I look at this dial, right? Again, this is code, right? So does anybody think these three dials are pictures? You can type in yes or no in the chat. Who thinks these are just pictures? Okay, y'all are smart. These are not just pictures. These are dials that move. So this is part of the code. We have to create tools that allow us to calculate our code, to run our code, right? So now I'm going to set this dial all the way down to 0. So here's our job today. We have to create all three of these black holes. How would we do it? Somebody throw a number between 0 and 1 for setting the spin, the rotation of our black hole. Is it not spinning? No spin is 0. 1 is super, super fast maximal spin. Somebody throw a number. 0.87 and 0.68. Now, let's do an average of that. So let's say 0.74, right? It's about in the middle. Okay. So simulation time means another dial. How long do we want our black hole to spin? This is on the order of seconds, right? So we're looking at between 100 and 5,000 seconds. How much time do we want? Okay, I see very specific, 1239. We got another number, something higher number than that. And if we don't get another one, we can do, okay, 3427. That's very specific. All right, 34. We're going to try to get to 27. It won't let me. Well, 30. Close enough, right? Okay. Now, do we care about the electric charge of a black hole? We're going to come back to this one. And if you are paying attention, we have a nice little button down here that says Start Simulation. And you see things flashed, which means something calculated, right? If we come back down again, our non-rotating black hole, do we think that the image of this black hole, the calculation of the non-rotating black hole, is going to be different from the rotating black hole? Put in the chat, yes or no. Okay, it should be different, right? Now let's check it. Uh-oh. Does everybody see this right here? You are looking at a mathematical model. Yes, this is 3D. We said we were going to do 3D work today. You are looking at the inside, mathematically, of a black hole. This is what a black hole looks like. This little orange disk at the very center, right? That is where the event horizon lives. You cannot cross that. That is the singularity of a black hole, right? Inside of that is our singularity. Now, again, this was our non-rotating black hole, right? So this should look different than a rotating black hole, right? Why do they look the same? You can throw in the chat or come off mute. Why do they look the same? Why are they the same? Yeah. Cameron, you are on it today. Yeah, it is because the shape of the black hole, right? So despite it rotating, the shape stays the same. Did our rotation change? No. Our rotation stayed the same number. So the shape of the black hole should change. Now, can we make the black hole faster? If I make the black hole spin faster, is this going to change? Yes or no? Very quickly in the chat, yes or no? Okay. Somebody says probably not. Let's try it. All right, so we need a number, another number between 0 and 1. Give me another number between 0 and 1. Oh, well, we're going super high, 0.93. All right. We're going to try to get there and boom. Close enough, right? Now, simulation time. Do we want to change that? If we want to change it, put another number. Nope, we keep it the same. Okay. All right. Start simulation. Who thinks the image is going to be different? Oops. My computer already told me. So how has this changed? How did this change? What's the difference? They're spheres now. Yes. So this is a black hole. And now another thing that you can see is that it's not entirely a total sphere, right? So if we look at it and John, you can kind of see at the poles here, it kind of squishes down, right? So that is what we call, and I'm going to put it in the chat here, the actual shape of a black hole is called an oblate spheroid. Oblate spheroid means that if I look at the top of a black hole, top down, right? And this is just, there's a cutout, looks like a pie. It looks like a circle. If you take a basketball and you look top down, you're going to see a circle. Looks like Pac-Man, exactly. That's the whole point. Now, but if you look at it kind of from the side, right? You see this dip in the middle, it squishes. So it's shaped a little bit more like an egg or a football. Not so pointy on the sides, but it squishes down. Why does it squish down? Somebody take a guess why it squishes down in the chat real fast here. That's a very good answer. Not quite though. It's squished down because it's rotating. So when objects rotate, nature, physics tells us as you rotate faster, you're going to squish smaller and smaller. You're going to squish closer and closer to the center of gravity, right? And you can test this at home. Don't take my word for it. Yes, I'm a professional, but test it at home. Sit in a chair that rotates just like this, right? And spin around. Put your arms out just like a rotating skater. Put your arms out. Make sure you have enough space. You don't hit anything. Put your arms out, rotate around, and then as you're rotating, pull your arms in. And I guarantee you will spin faster. That means that your center of gravity is moving closer and closer towards what we call our axis of rotation, right? So I'm being squished. These are centripetal and centrifugal forces. These are forces of nature squishing you down. The Earth is not a perfect sphere. Don't let anybody lie to you. The Earth is not a perfect sphere. It is an oblate spheroid. You may not be able to tell from some of our pictures, but I guarantee you the distance from pole to pole and one side of the equator to the other side of the equator are not the same. It's an oblate spheroid. Now, the Earth does not have these dips like the black hole does, right? It's not spinning that fast. But the black hole now has these weird dips in it. And now you can see every type of surface that's kind of inside the black hole. I'm going to keep throwing some keywords in the chat here. This is what we call a hypersurface. It is a mathematical or an imaginary boundary that you can cross if you're near a black hole. You're not going to see it. They don't exist. They're kind of like state lines. They only exist on the map, but not in real life, right? But these are mathematical, these are boundaries in physics, in nature, where we know certain physics happens and where it doesn't. That's a hypersurface. So if you go home and you go talk to your friends and you want to show off in school the next day or tomorrow and you say, hey, do you know what an event horizon is actually called? Tell them it's a hypersurface. And they're going to look at you crazy, but you're going to be smart because you learned hypersurface in this workshop today. So again, these are the real terms that us professional scientists use. These are the real things. So we're not sugarcoating anything. I'm not giving you, more too simplified words or keywords. These are the real things, real words that we're using. Hypersurface, another word for you to go look up. So you got some homework. We're building a word bank here for you to look up so that when you go to your friends and you talk about what you learned today, hypersurface should be one of those things. Now, the other thing for a black hole, right? Question for everybody. Type in the chat, yes or no. Do things spin or orbit around a black hole? Yes or no? Okay, we got one yes. Okay, seems like people are in consensus here. Yes, there are things around the black hole. Can we see them? Yes or no? Another question. Yes or no? Can we see them? Can we see what's rotating or orbiting around a black hole? Okay, we got one yes. Nelly, one yes. Okay, so we are going to calculate today how things orbit around a black hole. This is only a piece. This is a small fraction of this code. Everything else is hidden behind these menus. And if I were to expand all of this out, right, you can see what the actual code looks like. These are real numbers that you're seeing to calculate the black hole. So you're looking at real code here. This is my actual code. This is NASA code that I will be submitting and publishing as part of my own research. What else do we need to calculate? Well, we need a whole bunch of other funky stuff like this, right? Oh, no. All of this code is used to calculate the geometry of a black hole, right? This is a lot of math I had to learn. A lot of math. And we're still not done yet. We are still not done. There's even more code for us to learn, right? Now, we're not going to go through every single step today, but again, this is to illustrate all of the many different lines of code that we have to generate, that you have to go through line by line. Wrote this up line by line, right? To get us here. Now, let's go back up to our simulation time. We said we ran this, we solved this for 3,400 and about 30 seconds, right? That means we should have, how many data points should we have? Should we have 3,430 data points since we have 3,430 seconds of computation time? Yes or no? Is that going to be the number of data points that we've generated? Right. Who think it's going to be less than 10,000? Less than 10,000, put a yes. If it's more than 10,000, put a no. Who think it's going to be 10 million? Is that too high? The anticipation, I'm sure, is killing everyone. All right, so now let's actually look at what does it do? Please tell me it's not 10 million. Well, it's not 10 million. In fact, what I didn't tell you, this is about 10 million. To generate this 3D image, you probably need on the order of 10 million data points to generate all of these surfaces. So that was a trick question. You've already seen the data of 10 million. You've already seen what 10 million data points looks like. That's this geometry here. This here, right, is what we call particle orbits around a black hole. And you can see at the very center here, right, at the very center, you can see a black sphere right in the middle. If a particle were to orbit around a black hole, that is the path it would take. What does it look like from the top down? It looks like this. So if we looked at the black hole, we took a black hole and we looked at a bird's eye view straight down. That is what a particle would look like. Wisping around the black hole, right? Going around the black hole. Now, one thing that we are not accounting for here, and that is very, very hard to do, is whether or not the black hole went into the event horizon. That is extremely hard to code up. We're not going to cover that today, and I did not take the time to actually solve those equations to show you. But as you can see, the math is very, very complex. We would need a supercomputer to run those calculations. All of these calculations are done on my MacBook Pro. That's all you need to code this up. How many data points are we looking at here? Just take a guess in the chat. Throw a number in the chat. Okay, somebody, Trinity thinks it's 12,000. How many? Okay, think 7,000. Now, what if I told you it was actually 3,430? Each time step is a calculation. A calculation. The computer creates an orange dot at every time step. It calculates a dot. You're looking at the connection. Then the computer drew a line through all 3,430 of those dots to create this path that the particle takes. You could turn this data into a movie and see the particle go dot by dot, where the particle goes around the black hole. And this is what it would generate. I know. Now, what I didn't do, and it was a trick question, because I never said the actual number of the data points. There's a reason why we gave a very specific number up here for simulation time. Now let's really turn the crank on this and turn it up. We're approaching almost 5,000. Run simulation again. Is our plot going to change? Clearly our geometry didn't change, right? Because we didn't change spin. But the number of data points should change. Yes or no? Throw it in the chat. Yes, it should, right? This looks really weird, but it looks very correct, right? And now you can see when we run the simulation for a longer period of time, you can kind of see it starts to behave very symmetrically, right? This is what we call well-behaved. It gives us a pattern now. So you can see the orbit of the particle going around in circles, many different circles around the black hole. Now in the 3D version, we should see this in the 3D version, right? So now if I go top down, again, it's the same image. Look at that. That is what we call a beautiful graph. This is me geeking out on a Wednesday evening looking at codes about black hole. This is what I do, both on my free time and at work. So would I be writing this code whether or not I got paid for it? Yes. So This is why I always tell people, whatever you do in your job, if you're not having fun, find something you enjoy. Find something that you would have fun doing. To me right now, coding this up, I had a lot of fun. Was it hard? Yes, you can see, and I have not even expanded everything here yet. You can see all the many different lines of code. You can even see code that doesn't work. This is a failed attempt, and I have to fix it. Again, I told you that my code broke. So this is part of doing the science, right? Again, you're seeing all of these lines of code just so that we can get here. But is this the end of the story for describing what particles do around a black hole? It's not the end of the story. We generate other data. Again, now, very quickly in the chat, how many dimensions of space-time did we work in? Are we working in just 3 dimensions of space-time, or are there 4 dimensions of space-time? Okay, Cameron, you've been reading. 4 or 5. Yes, some people do work in 5 dimensions of space-time. That is what we call, and I'm gonna throw it in the chat here, another keyword. It's called de Sitter space-time. So that's another weird space-time where a thing called the cosmological constant now turns on. And now we're worrying about the essence of space-time, whether it contracts, it expands. Is the universe expanding? Is the expanding accelerating? Those questions now come into play for what we call de Sitter or anti-de Sitter space-time. That is not what we're covering today. What we just did is look at 4D space-time. If I had a particle, the red line, right, is what the particle is doing from 0 all the way to the end of our simulation. You can see that it almost escapes, right? This green line here, you can see how the green line goes up and down, up and down. Now, according to our graph, why would that green line go up and down? The green line is tracking the data for the particle, right, in a plane. If I had a particle that's circling around something, does it look like it's repeating? Does it look like it's repeating up and down? If it circles around something? Yes or no in the chat? It should, right? This is another thing that you can test at home. You can create a pendulum. You can take a ball, take a string, tie it to a rod, right? You place it on top of something, and you put a pencil or a pen at the end of that ball, and you put a piece of paper at the bottom, and you let the pendulum swing. You will see a graph that looks something like that green line. This is what we call periodic motion. If I am traveling in a circle, is that periodic motion? Yes or no? Say it in the chat. Oh, yes, question mark. Okay. It is periodic motion. Why is it periodic? If you start somewhere in a circle and you go all the way around, do you end up where you started in a circle? If you travel all the way around, you should, right? Unless you start somewhere in a circle and you travel all the way around, and then you kind of branch up and you keep traveling and you keep traveling like a spiral. Is that periodic motion? Yes or no? It should be, right? We see that here. You can see that here in the graph where it looks like the particle had a very tight spiral in the center, right? So it's in the data. We can see that. So data and graph confirm the same thing. They're talking about the same things. Now, in order for us to now really quantify many different types of orbits, right? You are looking at the many different types. What if the spin of the black hole changed? What if the mass of the black hole changed? What if the geometry changed as the particle was orbiting around the black hole? This is what our data would look like, right? It would look something like this. And you can kind of see where the particle comes closer and closer to the event horizon, then it skips out. And then it comes back and it dips under and then it escapes. These are all these colored lines. And you can see as you get slower and slower, you kind of mark right there, right? You kind of get trapped in these hypersurfaces, these event horizons. This is what this graph is telling you. Now, let's turn this all the way up. Let's turn everything all the way up. What happens if this number gets to 1? I want you to type your theories in the chat. You're theorists now. Type your theories in the chat. What happens when this spin value, when the rotation gets maximum, 1? What happens? Do things change? All right, something is supposed to change, right? Whoa. Where'd the other surfaces go? Yes, you know what? I'm Camry, if I was in person, I would like give you 1,000 NASA stickers. Both of you are on fire today. Yes, it points more inwards. You can see this now, right? What happened to our orange disk? Where'd the orange disk go? It's on the edge. It's on the edge of this inner surface inside. It's right on the edge there, right? So it kind of got larger. But in the center, it said, nope, I don't exist. So this is part of the problem, part of the mystery for black holes. A value of 1 means that the black hole is spinning as fast as it can, naturally, as fast as it can. It's spinning as fast as it can. Did it collapse in on itself? We don't know. Come back in another 10 years when I have worked out the math. But the very short answer and the very clear answer is we don't know yet. We still have to work the math. Now, what about our particle orbits? What do they look like? Should those change? Yes or no? Okay. Uh-oh. Woo. Now, whenever you see red like this, right? Red means that we have an error. Error, error, error. There's a red box there, meaning something was not able to be calculated. And if we go through our code here, this is part of how you would code. You have to check every line. You need to check every line to see where there's a 0. I'm going to throw very quickly in the chat an equation. And this is, or a question for you. What is 1 divided by 0? What's 1 divided by 0?
Also, just very quickly, sorry to interrupt.
Mm-hmm.
Once you all finish this, is it okay if I put that survey in the chat we're coming up on?
Yep. I'm going to end here quickly so you have time for the survey.
Oh, no worries.
Yeah. Okay, y'all are on it today. We do know what 1 over 0 is. It's infinity. 1 divided by 0 is infinity. Your calculator. Not all calculators are able to calculate 1 over 0. Haha, yeah. There's a trick question. 1 over 0 is infinity. But what does that mean to us, right? What does that mean to us? It means that one of these surfaces, remember, what did we call these surfaces? It was a very specific word that I want you to type in the chat. What did we call these? It's got a specific name. Starts with an H. See if y'all are paying attention. Yes, Trinity, it was hypersurface. Hypersurface. Now, where did it does sound like something from Star Wars? It does sound like something from Star Wars, right? But where did they go? They collapsed, meaning the math didn't work out. This tells us that the math didn't work out. Now, and if we were to actually look very, very close, if you can zoom in on your computer, on your screen here, you might see a dot at the very center of this calculation. That is where our calculations disappear. That's where the computer said, nope, I can't do this. All right, so last thing we're going to do. Last thing we're going to do, it quit. Yes, it did. Last thing we're going to do. What happens when this value is over 1? What happens here? We're going to set it to over 1. Is it going to break the computer? Let's hope it doesn't crash. Oh, something calculated, right? Last thing we're going to see today is this. This looks very weird. Now, this looks like a donut. There's a hole in the center. Now, I'm going to type in the chat. This is the last keyword for the day. You can go look it up. It's what's called a naked singularity. This is where our known physics of space and time and reality break down. This is where the actual mathematics breaks down. We do not know the calculations for this, which is why this graph looks weird. And if we keep scrolling down and keep scrolling down, our computer went haywire. It doesn't like it. We reached a whole bunch of ones and zeros. It doesn't like any of that. This is a naked singularity. This is what a black hole would look like without an event horizon. Now we're going to end there. I'm going to stop sharing so that you have time to kind of consume everything that we did today. And I'm sure you're going to have a survey at the end of this. Anybody have any last minute questions? Shane, you have a question. You can type it in the chat or you can come off mute really fast. We're going to take these last two questions. The
Shane
sites.
isn't going to unmute. I wanted to ask, what, hold on, sorry, what was my question? What site did you use to do this programming?
This is not a site, but it is what's called a computer algebra system. So this is what's called Wolfram Mathematica. It is software that I use that allows me to type in and compute equations and math and very complex mathematics and to generate graphics, video, audio, pictures, animations, presentations. It does a lot of things, but it helps to calculate very complex mathematics. So it's not something that you're going to typically see in your school. It is fairly expensive software that us professionals use to help us calculate the math. After we've done it, either on paper or on chalkboard, you can see this is real, right? So that's my work behind me. This is what I do every day. But that's called Wolfram Mathematica. So you want to learn about it? You can message me and I can probably share some, give you some links to some demonstrations that Mathematica has, and you can play around with it. Okay. Any other questions before we end here? I think we have last 2 minutes. I think we're going to end here. Okay, well,
Awesome.
I'm gonna turn it back over to you.
Yes, thank you so much. If you all can use the virtual hand claps or get off mute and let's give Dr. Gamble a hand clap as well. That was awesome. I really enjoyed every single part. I learned a lot as well. So what I'm gonna do is I'm gonna drop in the